Okay, I'm afraid we have to do this without the camera because it's not working. Luckily we have some music today. Okay, we're gonna try and do the empirical project assignment number 4 today. So let me see where it is. Empirical project assignment number, well, let's not do 4. We've done 4, let's do 5. So we're opening 5 on long run economic growth. And today what I'm gonna do is I'm gonna do this one mostly in Stata. Not because it can't be done in Excel, but because I want to show you how this one is done in Stata. Okay, so let's first open Stata and let's open our data set in Stata. So we're gonna go and look for macro data Canada DTA. That's the raw data set. Whoa. Well, it runs a do file that was still on file, but that's all done now. Okay, so let's open a new do file. I might as well take an old one to copy the initial code. So file, open, new do file. Put that code here. Let me see if I need to do anything more. So if I run all those commands, it opens the log, it opens the data set, it sets year as my time variable, eliminates this more command, and we're all set. Let me first save this file as EMP5 for Canada. So I'm saving it here. And then the first thing I need to do is I need to calculate the average long-term growth rate of GDP per capita in my country and look at the deviations and discuss that. So the first thing I need to do is I need to generate the GDP per capita and the GDP per capita growth. So I use the commands, might as well do it directly in the do file. Put that here. Generate, let's say GDP per cap, and that's defined as the GDP in constant prices divided by the population of my country, which is here, population number. So put that in here, and then I generate the growth rate of that GDP per capita. GDP per capita growth rate as GDP per cap minus the lagged value of GDP per cap divided by the lagged value of GDP cap. If I execute this, it says the log file is already open. I have to put close log here and do it here as well. There we go. Now if I run this, it works. Okay. Of course I can summarize the GDP variables and see what GDP cap, what we got. And this is the GDP per capita. Mean is 0.03, standard deviation 0.005. And we can also look at the, of course, the summary table for GDP growth. Which is around 1.8% for Canada over the period that I have data. Its standard deviation is 0.2%. Sorry, 2%. And its minimum is -4% and its maximum is about 6%. So that gives me some information as requested about this, this question. Well, discussing that is relatively simple. I can basically use this table. Copy as picture, plug that in here. GDP per capita calculated as the GDP co over pop, and then computing the annual growth rate gives us a variable that varies between -4 and +6% at an average growth rate of 1.8% and a standard deviation of 2%. What that means, by the way, just as an additional piece of information, I don't expect you to write that down, but I can tell you now, is this standard deviation means that for a normally distributed variable, about 67% of all the observations would lie between 1.8 plus 2.2 is 4, and 1.8 minus 2.2 is minus 0.4% growth. So in 2/3 of the years you would be between those limits. And then you can extend it with one more standard deviation for the 90, I think it's 2%, and then 99% is between 3 standard deviations. So it gives you an indication of how volatile this growth rate is. Okay, what is the average saving and average investment rate in your country, and what does it mean if they differ? Well, let's first compute them. We go back to Stata. So here, what I've done is I've used the summary table, GDP-CG, that gives me the results. So this would be question 1, and then we turn to question 2, saving and investment rate. Okay, so how do we compute our saving rate? We generate the savings rate, so let's call that variable SAV-RT for savings rate. What we need is the savings. Let's see if we have savings. That's not directly in our data set, so we have to generate it first. And the way to do that is, of course, we need total savings in the economy. So let's first generate a variable that we call savings for the public sector. And the savings for the public sector, that's the taxes that we have in our data, minus the government expenditures, which we also have in our data. And we can generate the savings of the private sector as the income, so that's GDP in constant prices minus the taxes in constant prices, that's your disposable income, minus your consumption, that's your private savings. And then you can generate your savings as the public savings plus private savings. Of course, you can also do it directly. You have then GDP at constant prices minus the government consumption minus the private consumption. Alright, so that's my national savings. And then the savings rate, savings rate is of course my savings level over GDP. So that gives me that expressed as a rate. And for investment, we need the investment rate. Perhaps I should turn the music down a little bit. Sorry for that. So then the investment rate is of course the total investment in the economy. So that's EMP5 over the GDP. So then I have my savings and my investment rate. And the question asks me to compare those. So to see whether they're equal. And one way to do that is to simply plot them against each other and then see if they're on the 45-degree line. That's one way of doing it. There's not one right way of doing it, there's multiple. But if I do that, I get this nice graph with the investment rate and the, of course I don't want to scatter it with SAV-CO, I want to scatter it with the SAV rate. So now I have the scatter plot, which I can copy and hopefully also paste. Yeah. So then, of course, this does not tell your tutor what you've done, so you have to tell your tutor what you've done. In the plot, we see the saving rate defined as private plus public savings over GDP plotted against the investment rate. It is clear from the graph that the two are not equal. Now you have to think what that means. What does it mean when they differ? They can differ because Canada is an open economy and domestic savings need not be equal to domestic investment. In points where in points below the 45-degree line, it says this is point 22 and this is point 22. This 45-degree line is most of the points are below the 45-degree line. Savings exceed investment, and this implies, so there's more savings in Canada than there is being invested. That means that they're exporting more than they're importing. This implies there is a surplus in the current account. So there we go. Anything else? No, that answers that question. Using the data on capital formation and depreciation, compute generate the change in the capital stock over time. Okay, so let me quickly save this. I don't want to save it as assignment 5, I want to save it as empirical project 5 for Canada. And let me save it there. Okay. Let's go back to Stata. And then the question is, how do I... Question 3. Question 3 requires us to generate the capital stock generate the change in capital stock. Now, the change in the capital stock in Canada, we can generate the delta capital stock, let's call it that, as the difference between the investment in any given year, that's gross investment, minus the depreciation. It's in the data set. Depreciation, DEPCO is over here, INFCO is over here. So this is our net investment. Oh, let's do that. So now it's generated that data. And we can summarize D caps, and you can see that well, typically it's positive. So the capital stock is increasing every year. And now what we can do is we can generate, see if that's a question, the change in capital stock and discuss what this variable means. Oh, well, okay, so I've generated that variable. Maybe it's useful to show the tutor what I've done. So if I give the command sum D caps and run this thing again, then from here I can basically copy all this as a picture, and then by inserting it here I basically have everything the tutor needs to see what I've done. Of course, I need to reflect on this. I need to say, what does it mean? What does this variable mean? Well, what does this variable mean? This variable means that in Canada the capital stock has increased by 68849 Canadian dollars. This is Canadian constant dollars because everything was in constant dollars. So it's of 2007, I think. I would have to check. On average per year. And the capital stock has grown. No, that's what it means. Okay. Of course, the variable itself, reflects the annual increase in capital. So it would be the net increase. Okay, now, so if we assume that the initial capital stock is 0, so question 4, we assume the capital stock with an initial value of 0, then we can basically construct a capital stock by simply summing up this variable. So here goes question 4. Generate, and in the lecture I called this the quasi-capital, so I'm going to call it quasi-capital stock here. Okay, I'll call it quasi-capital stock, so that's Q cap stock. The quasi-capital stock is going to be defined as the sum, that's a command I can use, of D caps. And what this command does is it sums all these values over time, because I've defined time as my time variable. Okay. Now, of course, I want to see this thing. I get a picture of that. Let's call it Q caps and year. So let's just put it in a graph against year, and then, hey, we start at 0, 1970, and it increases nicely to about 3 million in the last year. So that's the net, the sum basically of all additions to the capital stock. Now this is a nice graph, so I'm gonna use that here, and I'm gonna tell my tutor what I've done by using the command sum. We constructed the sum of net capital investment under 3 to obtain the variable Q caps presented in the graph above. Okay. Okay, plot the growth rate of the capital stock. What's the general tendency do you observe? How do you explain it? Okay. So now what they're asking us to do is to look at the growth rate of this capital stock. So we have to construct that growth rate. Question 5, generate growth of quasi-capital stock. Generate. We know how to generate a growth rate by now. Q cap growth rate is given by Q caps minus the lagged value of Q caps over the lagged value of Q caps. And we needed to plot that too. So here we go. Boom, boom, boom. There it is. And we can copy that into the picture. Okay. Computing the annual growth rate in Q caps and plotting it against time gives us the picture above. Now, what do you see in this picture? Well, it's dropping very rapidly. The growth rate is dropping rapidly. This makes sense. Why does it make sense? Rapidly. This makes sense. Because starting from a 0 initial level of capital implies the growth rate is very high at the start of the period. Well, if you start from 0, the growth rate is going to be infinite. Okay, so that answers 5. Let's go to 6. What is the depreciation rate if you assume it constant over time? Use the fact that total depreciation increases falls when the capital stock increases falls. Is that value reasonable? Why not? Well, here you need the trick that I explained in the lecture, because what we know is that depreciation is equal to delta times k, right? Depreciation at time t is equal to delta at time t. So if we assume that it's constant, then we also know that the change in the depreciation rate is equal to delta times the change in the capital stock. And we know, this is more important, that at any point in time, the and we know that this is equal to delta times K0 plus the quasi-capital stock at time t. Because K0 plus the quasi-capital stock, whatever K0 is my capital stock at time t. Well, if you're using this formula and rewrite it a little bit, then you can take the depreciation at time t divided by delta, and subtract K0, and that would be equal to the quasi-capital stock at time t. And if I write that the other way around, what appears is 1 over delta times depreciation at time t minus K0, where K0 is a constant. And this is a regression equation. To show you that, it's an equation I can regress. Let me write it like this. This is an equation I could estimate. So using the fact that boom boom boom, we can regress this equation. Okay, make this all red. Go back to Stata to run that regression. So what we need to do is, for question 6, estimate the depreciation rate. What we need to do is regress. So my dependent variable is Q cap S, I think it's called, yeah, Q cap S on DEPCO. Let's see where that leaves us. So we have now this regression. Oh, I don't want it that way. Let me go back, copy it as a picture, put it here. This regression implies the average depreciation rate in Canada is 1 over 15.98. Well, we need a calculator to do that. So 1 divided by 15.98 15.98. That gives you 6.2%. Is 6.2%. Okay, is that value reasonable? Why not? This value is reasonable, as we would expect it to be between 5 and 15%. For Canada, the capital stock seems to consist of capital goods with a long economic lifetime on average. So it's at the lower end. But it's a reasonable value for Canada. You know, Canada has a lot of logging and resource extraction industry, mining industries, stuff like that going on. So there the capital stock is relatively long-lived. I guess wear and tear on the roads and the infrastructure in Canada is not that high because it's not a very densely populated area. So you can make some arguments why this would be reasonable. All right. So by the way, also you see a very high fit, and we know that the initial capital stock, can also be obtained from this regression and is equal to, well, minus that level, so it's 1.104 and 9247. Well, and then probably that's in thousands of Canadian dollars, maybe even millions. I think everything in the data set is in millions. So that would be about 1,000 billion. Okay. Use the results sub 6, these results, to estimate the initial value of the capital stock and recalculate the capital stock you found sub 4. Recalculate and plot the growth rate of the capital stock. What's the general tendency now and how do you explain the difference? Aha. Okay, save this. Let's go back to Stata. So now for question 7, we need to compute the capital stock. And basically, that's rather simple, because we need to generate the capital stock by taking the quasi-capital stock, the quasi-capital stock, and adding the initial capital stock for 9247. Yeah, we got some, yeah, okay. And then what they ask us to do is look at the cap growth rate, the capital growth rate, and of course that's equal to caps minus the lagged values caps over the lagged value of caps. And they again want us to show the difference with the earlier result. So let's put the same figure in there. Boom, boom, boom. And then we have this picture. And of course, That's what we were hoping for. By adding the initial level of capital to the quasi-capital computed under, where was it? I think we computed it under 4. And computing the growth rate, we obtained cap GR that is displayed in the figure above. It shows the growth rate of capital fluctuates. It fluctuates and varies between 2 and 5%. 5%, not unlike the GDP. Something you might notice. Okay. Now what they want us to do is plot the log of the GDP per capita against the log of capital per capita, and can you find proof of diminishing returns to capital? Okay, well, it makes sense to give some thought to that. What would be the evidence you would like to see? Or if you're plotting the GDP per capita against the capital per capita, you would expect a concave line, a concave relationship if there's diminishing returns to capital. If we plot this log against log, then it would be a straight line, but its slope would be less than 1. Okay, so let's see if we can get Stata to give us that. Of course we can. Question 8. Plot GDP against capital per worker, per cap. So it's capital per capita. So just to avoid any confusion, let's call that POP for population here. And then so we want to generate cap, I think cap K is the corresponding. We have GDP K and we have cap K. Okay, cap K is equal to capital stock divided by the population number. Is that a population number? Yeah. So we have the capital stock per worker, and then we want to scatter cap. So GDP against cap K. And see if we get a concave line. Boom, 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 boom. Well, we do. We find a nice concave line. GDP per capita is positive in capital per capita, but it's at a decreasing rate. And I think if we generate the log of cap K is equal to the log of cap K, and we generate the log of GDP per capita is equal to the log of GDP per capita, and we scatter those, or we might as well regress them on each other and obtain the slope coefficient. So we do GDPK. If we regress them on each other, we obtain the slope coefficient for that line, which is, as you can see here, 0.76, which is nice. Very relatively high, but it's nice. Okay, did that wrong again. See, it's getting late and dark. Well, you don't see that because the camera is off. But let's copy this as a picture and then comment on the results. Let's also put the graph in there. Since we've made it, we might as well use it. Copy graph, paste. We have computed the capital stock per person and plotted this against the GDP per person above. This picture shows a clear diminishing returns to capital. This is also borne out in the regression of log capital per person. Sorry, that's log GDP per person on log capital per person, yielding a slope coefficient of 0.768. This coefficient, I'm going to again teach you something I'm not really expecting, but what you can see here in this regression output in the confidence interval is that in 95% of the cases, or the confidence interval of 95%, 1 is not included, which means that this variable, this coefficient, is estimated to be significantly lower than 1. Is significantly lower than 1. Statistically significantly lower than 1. It's also somewhat lower than 1 in economic terms, so 0.8 is rather high, is a rather high elasticity, but still. So this coefficient is significantly lower than 1. Confirming diminishing returns to capital for Canada. I mean, this is for Canada. I'm not sure what your results will be for your country. It's very possible that you might find a rather straight line instead of a curved line, and you might actually find that it's not significantly different from 1, or might even be above 1. What that means is that your country has experienced relatively strong technical change, improvements in the production function over time, such that the same level of capital generates higher GDP. But in Canada, it seems to be that is not a very strong effect. Okay. So now, in the honors or bonus question, the question is how much of growth in GDP per capita cannot be explained by growth in capital per capita? Assume production elasticity of capital equals 0.4 and see the appendix to chapter 15. Now, if you assume that this elasticity of capital equals 0.4, that's rather strange if you've just estimated that elasticity to be 0.8. 0.76, but okay, if that's what the question wants us to do, then basically what we need to do following the appendix in chapter 15 is to compute the so-called growth residual or solo residual. And if I go back to the appendix to chapter 15, let me go look up if there is a nice equation there. It basically, it's on page 346. you see that the residual is equal to the growth rate of output minus alpha times the growth rate of the population plus 1 minus alpha times the growth rate of capital. So what we can do is we can write this function down, and alpha is in this case, well, the 1 minus alpha is 0.4, so it's 0.6 times the growth rate of a population. Sorry, I have to start with the GY. Minus 0.6 times the growth rate of the population minus 0.4 times the growth rate of capital. Let's call that K. That's the residual. Now, I can compute this quite straightforwardly in Stata. Compute solo residual. That's what this thing is called. Let me see, do we have the growth rate of capital? I think we have the growth rate of capital. We have the growth rate of GDP. Only per capita, I see. So that's a problem. We need to generate the growth rates. Okay, generate GDP growth rate is equal to GDP co minus GDP co, and of course that one lagged, divide by the lag of GDP co, generate the growth rate of the population. Pop growth rate is equal to pop number minus the lag of pop number divided by the lag of pop number, and generate the cap growth rate is equal to, and I think this one's called caps, minus caps. Well, I think we have that one. Capital growth rate is here. Yeah, so that's the capital growth rate. So we don't need to generate that one. And then we generate the residual. Let's call that thing residual growth rate is equal to the GDP growth rate minus the 0.6 population growth rate minus 0.4 times the capital growth rate. And then I want to scatter that against time, I guess. Just first have a look at what we're looking at. Ah, okay. Of course that doesn't work, and if I do this, then I have to close the log manually. It's getting late. So what we see here is, of course, that this residual growth is pretty much all over the place, between minus 5% and plus 5%. Let's see where we end up if we summarize this residual growth rate. Get a summary table of that variable, and you can see that indeed the average is very close to zero. The scatter, the variation is rather high. Wow. Okay. It's probably the last thing I'll do today. Okay, so what we've done now is how much of the growth in GDP per capita cannot be explained by growth in capital per capita, or population growth in this case. Of course, we can also compute a residual like this. I haven't done that now. Because if it's in per capita terms, I need to do it in per capita terms. So let's return to this. Then I think I have to generate the capital per capita. Well, we have capital per capita. I have to generate the growth rate of capital per capita. So there we go. And once I have that growth rate, I can basically generate residual growth rate 2, which in this case would be the GDP per cap growth rate. I'm not sure that's what it's called. I think there's an A missing. Let me double check. GDP CG, that's the growth rate of per capita GDP. So there's no R either. Okay, minus 0.4 times this variable I just constructed. Okay. Boom, 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 boom. Of course it works, but I should still produce a picture. Res growth rate 2 year and sum of res growth rate 2. And boom. Okay. Ah, that was a mistake there. Huh. Yeah, you gotta be careful how you do these do files. They are forbidding, which is nice because you have an automatic check on on the quality of your work. Okay, so here we have this table. Let's see what the differences are. And this picture. See, so they're very close together, these averages, which is basically because we're doing pretty much the same thing. I mean, if you would do 0.6 times the growth rate of population, or you're dividing everything by p, that's basically doing the same thing. So you can see the results are pretty much the same. So I'm going to write some comments here, comments on what I see and think about it and how I constructed my data, and then I am done. Right, so before I exit this, I go to my do file basically. Up, I copy it, paste it here, save the whole thing, send it off to my tutor, maybe save this do file and send it to him too, or her, and then we can exit Stata. Let's just not save, and we're all set and done. And I'll see you for the last one next week.